Hello, calculus fans. Let's talk about gravity and gravitational fields. Let's say we have two objects. Their masses are little m and big M. We have something called Newton's law of gravitation, and it says that the magnitude of the gravitational force between the objects is m times big M times g all over r squared. R is the distance between the objects, and g is something called the universal gravitational constant. This is an example of something called an inverse square law. Inverse because there's a reciprocal, there's an r squared in there, and it's a square law because of the r squared. So let's assume that the object with mass big M is located at the origin in R3. Let's use as an example here that big M will be the mass of the Earth and the origin is at its center of mass. So very often when we use Newton's law of gravitation, we'll think of little m and big M as being the masses of the small and the large objects. Let's let the position vector of the object with mass m be r, which is xyz. It's pretty common for physicists to use r for our position vector, and from now on we're going to use it quite a lot. So r is equal to the length of the vector r squared is equal to the length of the vector r squared. So the gravitational force that's exerted on the second object acts towards the origin, because that's where the center of mass is. And if we make a unit vector in this direction, it'll look like this. R over the length of r, but we have to make it negative, because we're pointing towards the origin, not away from it. So the gravitational force acting on the object at the point xyz is f of r, which is equal to negative m times big M times g over the length of r cubed times the vector r. That's because we're taking this expression and multiplying by the expression that we had on the previous page. Now we could also write this vector in terms of its component functions. We'll use the fact that r is equal to xyz, and the length of r is the square root of x squared plus y squared plus z squared. And then this is what f would look like. Notice in the denominators we have x squared plus y squared plus z squared to the 3/2. And so we've got things broken down into the I, j, and k components. And finally, let's take a look at a picture of a gravitational vector field. Looks pretty pointy. Notice everything points towards the origin, because if you have your big mass centered at the origin, then everything falls towards the origin. The closer you are to the origin, the more powerful the gravity field is, and so the lengths of the vectors will be longer. Okay, that's all for now.